Chapter 29, Theory Video 2. We are going to discuss about mass and energy and how it is involved in nuclear decay. Now we know that when an unstable nucleus of an atom was to disintegrate, that is to decay, it would produce energy. So in calculating, when we have to calculate the energy that is involved in this, we have to first consider the mass of the materials or mass of the particles in it. Now we have to we have to consider an unstable nucleus, but before that let's take a stable nucleus, carbon, for comparison purposes. Now in carbon we have 6 protons and 6 neutrons, and it is a very highly it's a highly stable nuclide. If it was not, then that would be a big problem for us, because we are made up of a lot of carbon. So the nucleons are tightly bound together with a strong nuclear force, and to pull them apart we need a very high amount of energy. So they don't naturally disintegrate because of its strength. Then here in this figure we have an imaginary experiment of what we have done. On the left hand side we have the single carbon 612 nucleus. On the right hand side we have 6 protons and 6 neutrons, that is by taking apart the nucleus or dismantling it. When we put these two onto each side, we expect these to balance, because on the left hand side you have 6 carbons, 6 protons and 6 neutrons. On the right hand side also we have 6 neutrons and 6 protons. But what happens is, the interesting thing is, the balance will tip to the right. So that means when you take the separate nucleons, they have a greater mass than the nucleus when it is put together. So that means the law of conservation of mass is supposedly broken. How can that be? Because it is a fundamental law of nature that we consider is true. When we now let's figure out what is happening here. When we take this 612 nucleus apart, we have to do work against. Now pulling it apart is not easy. We have to apply strong forces to overcome those strong nuclear force. Then because the nucleons attract one another with this very strong nuclear force, we have a lot of energy to put in. So this energy increases the potential energy of the individual nucleons. So that means nucleons within this nucleus is going to sit in a deep potential well that is going to be the result of the strong nuclear forces that hold them together. When we separate them, we lift them out of the potential well, giving them more nuclear potential energy. So this potential well is quite similar to what is formed when the electric field around a nucleus is considered. Now in the when you take the electrons, it is really easy to remove them because they don't have that much of a potential when compared to nucleons. It is easier to remove an electron than to remove a proton or a neutron from the nucleus. So now that is actually with regards to the energy and the energy wealth. However, the mass change is still the same. So Einstein developed a hypothesis about energy and mass, which he considered to be equivalent. Now, in the earlier lesson, we discussed that photons are energy packets, and they act as particles, and they act as particles means they act as something that which has mass. So this is another development on the same theory. uh, you know Even though it is something that we can say, but how are we going to prove it? The thing about this is, when a body or a particle is in a higher energy state, they have more mass than a low energy state. The thing about this is, when you take a bucket of water and when you carry it to the top of a hill, we say it has more mass than at the bottom of the hill, because when we carry it upwards, we have given it more energy, more potential energy. A tennis ball, if it is traveling at 50 meters per second, it will have more mass than the tennis ball which is going to remain stationary. This mass difference is quite small, really small. We can't actually notice it. However, we can actually, when in relation to these tiny nucleons, that in the nuclear physics, the charges are quite high in comparison to the size of these materials, these particles. So as a result, this change in mass becomes quite significant when it in relation to these microscopic particles. When you take uh, electrons, they can be accelerated to, because they are accelerated to speeds closer to the speed of light. We can clearly see how they affect. So this mass, the conservation of mass and energy, these are laws. So another way of putting this out into the open is actually combining these two. We can say that the total amount of mass and energy in a system is constant. In another aspect, we are actually going to, this is something that you need to understand, this is for your knowledge. We are going to the basic principle that everything is energy. Everything around us, everything is made up of energy. We are not things, we are just packets of energy which is concentrated. So it is something like a kind of an imagination, or something that doesn't really exist while it exists. So that is something that you might be able to solve. This problem you might be able to solve in the future when you become a scientist. So Einstein developed this mass energy equation. So this is one of the most famous equations in the world, and a lot of people who have no idea what physics is knows these equations. E equals mc squared. So c is the speed of light in a vacuum. The value of c is approximately 3 into 10 to the power 8 meters per second, but its precise value is 299,792,458 meters per second. So what happens is, We are talking about the change in energy in relation to change in mass. So we take the equation to be delta E equals delta mc squared. Delta E is the change in energy, delta m is in mass, and c is the speed of light in a vacuum. So you can write it in different formats: delta E equals delta mc squared, or E equals c squared delta m, or E equals mc squared. So this equation, whatever the format that it would be given, it refers to the Einstein's mass energy equation. So as you can see here, energy is equal to mass multiplied by the speed of light squared. So the mass of a system increases when mass increases, energy increases. That means energy is supplied to it, the mass would increase. The mass decreases when energy is released. So that there is a direct relationship. So now this is actually proof for us that total mass of particles before the nuclear reaction and their total mass after the reaction, why they are different. So the after the reaction means after they are separated, they have been done work. On those we have done work, and as a result, its mass would increase. So then. Now in this table 29.1, it gives the mass in kilograms of each of the particles in 29.3 figure. So let's look at this 29.3 figure. As you can see, on the left hand side you have the nucleus, 6 protons and 6 neutrons. On the right hand side you have the 6 neutrons and 6 protons separated. Right, so now let's look at this very carefully. One proton and the neutron and the nucleus. As you can see, the rest mass would be, they have given 1.672623, neutron 1.674929, and the C12 nucleus would be 19.926483. Now let's see whether they are these values are given in kilograms, and they are considered to be rest mass. That is the mass when it is stationary. If it was moving, like we discussed in the equals mc squared as well, if it is moving, it would have a higher mass as well. So we are not going to consider the mass that is gained by movement, but rather we are going to take when it is stationary. So these values are taken to a high degree of precision using mass spectrometers, and we have to take it to calculate and see. Now let's see mass of the system before. That is 6 into 1.672 into 623. That is, there are 6 protons, you multiply by 6, and the neutron mass also you multiply by 6, and you add them together. Then you will get 20.085312 into 10 to the power 27 kilograms. So that is mass of the system before. Mass of the system before. Then mass of the system after, that is the mass of, that means the nucleons, separate nucleons, put in together to combine this. Mass of the system after is 19.926483. So mass in the the decrease in the mass of system is 0.158829 into 10 to the power minus 27. So that means, so this is actually not separating this. So try to remember that we are talking about a separation. First you take the nucleus and then separate. But in this particular situation, we are talking about 6 neutrons and 6 separate protons are joined together to produce a nucleus. So then what happens is energy is lost. Energy is lost. When 6 protons and 6 neutrons combine to form the nucleus of carbon-12, there is a small loss of mass that is called the mass defect. Right? So the mass is lost. So the mass defect of a nucleus is equal to the difference between the total mass of the individual separate nucleons and the mass of the nucleus. So that is quite obvious. So you take the mass of all the nucleons separately and then subtract from the mass of it together, then you get the mass defect. So when there is a loss in mass, so that means energy is released. This mass is going to be released in the form of energy. So the energy release is given by the equation, Einstein mass energy equation, delta E equals delta mc squared. Now we know the mass, then we know the speed of light, then we will get delta E equals 1.43 into 10 to the power minus 11 joules. This is going to be a very small amount in an atomic scale, a single atom. Now, if you take the amount of energy released in a chemical reaction, that would be of a single carbon atom, that would be of the order 10 to the power minus 18 joules, which is million times smaller. So that means if you just burn carbon to produce carbon dioxide, that chemical reaction would be million times smaller. The energy is million times smaller. Just imagine turning that energy of a fire turning into million times, that would be destructive. Now let's look at the worked example 3. So here the data you should be determined to find the minimum energy required to split a nucleus of oxygen 16 or 16-8 into separate nucleons. So we have to give the answer in joules. So this is not exactly a very difficult question. Just follow the theory steps. So we have to first find the difference delta m in kilograms between the mass of oxygen nucleus and the mass of individual nucleons, because there are 16 nucleons and 8 protons. We have to multiply proton number and neutron number are the same. So you multiply the neutron number by 8 and add it to the sum of 8 protons. And then from that you subtract the mass of O16 nucleus, and then you will get delta M to be 2.20 into 10 to the power 28 kilograms. So here what has happened is now they are asking what is the energy required to split a nucleus. So external energy, because there is an increase in the mass of the system, we know that the final mass minus initial mass means there is an increase of mass. So as a result, we have to supply energy to split the oxygen 16 atom. Then we use the Einstein mass energy equation to determine the energy supply. Delta E equals delta mc squared. So this amount is going to be 1.9 into 10 to the power minus 11. So now this is actually the minimum amount of energy. If there was more energy, if we supplied more energy, then what happens is that surplus energy would convert itself into kinetic energy of the nucleons. Let's write down a note on this before going into mass energy conservation. Mass and energy. When a unstable atom decays, energy is released. This energy released has a direct relationship with the mass of the nucleus as well as the individual particles that makes up the nucleus. When protons and neutrons are to be separated from the nucleus, we have to supply very high amounts of energy to overcome the strong nuclear force which bounds them. This results in a situation where the work done to separate these protons and neutrons will put these separated particles into a high energy state. Higher the energy, higher would be its mass. This relationship was presented as an equation by Einstein. Put a command right down, E equals mc squared, where c is the speed of light in a vacuum. C has a value of 3 into 10 to the power 8 meters per second, or more precisely 299,792,458 meters per second.